Hey guys, this is CHEMPLIFIED and today we will talk about Raoult's Law. Since this is the second video on Raoult's Law, the name is Raoult's Law 2.0. Now, without wasting time, let's start our video. In the previous video, we talked about Raoult's Law for liquid-liquid system. In this video, we will talk about Raoult's Law for solid-liquid system. Now, by solid liquid system we means there is one non-volatile substance and this is your solute. It is also written for a solution of non-volatile solute. The solute is non-volatile and solvent is volatile. So Raoult's law states that for solid liquid system, for a solution of non-volatile solute at constant temperature, vapor pressure of a solution containing a non-volatile solute is proportional to the mole fraction of the solvent, which means the solute particles will not have any effect on the vapor pressure of the solution or on the vapor pressure of the solvent. Now I repeat again, what is the meaning of non-volatile? Non-volatile means substances or liquid which do not want to evaporate. Non-volatile means which do not want to evaporate or which cannot be evaporated easily. Right? For example, now since we are talking about solid liquid system, solid substance which are non-volatile are like sugar and salt. The vapor pressure will be only of solvent, but still this non-volatile solute will show its effect in the solution. We will talk about that later. So what is Raoult's law for solid liquid system? At constant temperature, vapor pressure of a solution containing non-volatile solute is proportional to the mole fraction of the solvent. Right, let's move ahead. For a non-volatile solute, PB naught is equal to 0. This is important. Why PB naught is equal to 0? What is PB naught? PB naught is vapor pressure of pure component. In our case, we are talking about component B. So, vapor pressure of pure component is equal to 0. In our case, non-volatile solute. What is the non-volatile solute? Which do not want to evaporate. That's why, since the solute is not trying to evaporate or is not easily vaporizing, its vapor pressure in pure state will be equal to 0. For example, sugar. You put sugar and you raise the temperature. You will find that it is not evaporating easily. You need really high temperatures. Right? So non-volatile solute will not evaporate and we will consider that their vapor pressure in pure state is equal to 0. Now, according to Dalton's law of partial pressure, pressure of the solution is equal to mole fraction of A multiplied with vapor pressure of pure component A plus mole fraction of B multiplied with vapor pressure of pure component B. Now, since PB naught is equal to 0, value of this is equal to 0. The whole term will be vanished from the equation. Now, solution's pressure will be equal to mole fraction multiplied with vapor pressure of pure component A. That is our solvent. Yes. Now B is non-volatile. A is our solvent. Right. So total pressure is equal to the partial pressure of A. Why? Because partial pressure of A is equal to mole fraction of A multiplied with vapor pressure in pure component. This is your partial pressure. Now X, Xi A and P naught A are already written in this place, right? Now Xa can also be represented as this is nothing but mole fraction formula. In place of 1 you can write Na A plus B, right? Now let's come to our main equation. We know that total mole fraction value is equal to 1. We will derive some more equations. Xi A is equal to 1 minus Xi B. Substitute this value in our equation. We will get P solution is equal to 1 minus xi b multiplied with P naught A. Again continue with the multiplication. PS is equal to P naught A minus P naught A psi. After interchanging a few times, after interchanging the equation a few times, wait a minute. After interchanging a few terms from left hand side and right hand side of the equation, we will get P naught A xb is equal to P naught A minus PS. Now this P naught A minus PS have a positive value, which means, I repeat, if P naught A, vapor pressure of component A in pure state, minus total pressure of the solution, if the value is positive, it means P naught A value is, it means P naught A is greater than PS, right? Which means in this case, pressure of the solution will not increase. In this case, pressure of the solution will not increase, because pure component have higher vapor pressure than vapor pressure of the solution. Now this term P naught A minus PA is also known as lowering in vapor pressure, which is one of the colligative properties that we will discuss in the upcoming videos. P naught A minus PS shows lowering of vapor pressure, and the colligative property which we will discuss is relative lowering of vapor pressure. This is not relative lowering, this is just lowering in vapor pressure. The value will be given as P naught A minus PS, where P naught A is vapor pressure of pure component A and PS is vapor pressure of the solution. Relative lowering of vapor pressure is in relation with some other thing. We will talk about that in the upcoming videos or in that topic. Just remember, for this particular video, P naught A minus PS is lowering in vapor pressure. That's it, right? Now let's move. Remember a few things. When a non-volatile solute is added to a volatile liquid, in simple words, you are adding sugar to water, right? Sugar is non-volatile, water is volatile. Its vapor pressure decreases. We talked about P naught A minus PS. Its vapor pressure decreases because less number of solvent particles present in the solution at the surface as compared to pure solvent. What it means? Now consider our container. This is our container, closed container. Now in this container only component A is present. If only component A is present, the gas formed or the vapors formed will be of only component A, right? So this is vapor pressure in pure state. Now consider another container. This is also closed. Now you dissolve a non-volatile solute in component A. In this case, what will happen is non-volatile solute particles will also be present at the surface, right? This is A particles and this is B particles, non-volatile solute. B is non-volatile, right? Try to understand this. In this case, all the particles on the surface were of component A, so they evaporated easily, right? So the vapor pressure were also in larger amount. But in this particular case, our second case, this is our first case, this is our second case. In this particular case, two different types of particles are present on the surface, due to which the availability of particle A decreases at the surface, due to which the vapor pressure of the solvent decreases or the solution decreases. Because as the number of particles on the surface, on the liquid surface decreases, the number of particles going out as vapor will also decrease. So a non-volatile solute decreases the vapor pressure, which is known as lowering in vapor pressure given by this formula, right? Remember this term. Lowering in vapor pressure is given by P naught A minus Ps, where P naught A is vapor pressure of pure component A and Ps is vapor pressure of the solution. So that's how vapor pressure is lowered, right? Let's move. Now what happens is vapors formed and vapor pressure of the solution decreases due to the presence of, I repeat, due to the presence of non-volatile substance or non-volatile solute at the surface. Due to the presence of non-volatile substance at the surface, the overall vapor pressure of the solution decreases, and this is known as lowering of vapor pressure. I have already told you P naught A minus Ps is equal to delta P, where delta P is change in pressure, or to be precise, change in vapor pressure, right? Since P naught A is larger than Ps, the value will be positive, change will be positive, and we have a lowering in vapor pressure. Alright, I hope you understand Raoult's law for solid liquid system also. This will be it for today's video. Thank you for watching.